Hello and welcome. My name is Haibin Zhao, for Chair of Pervasive Computing Systems at Karlsruhe Institute of Technology in Germany. In this talk, I will introduce you a printed electrodemo activity sensor with optimized filter for stress detection. This is joint work with the Institute of Nanotechnology, also at Karlsruhe Institute of Technology. It is known that the chronic stress does harm to human health, and it decreases their feeling of happiness. Sometimes it even reduces their productivity in working. Therefore, long-term, continuous, and unobtrusive stress detection becomes important. Currently, the wearable devices for stress monitoring are usually smartwatches and wristbands. However, they still suffer from some shortcomings. For example, they are usually pricey, and moreover, their non-flexible housing and large size prevent them from high variability. In this regard, printed electronics becomes a powerful candidate in wearable stress detection devices, as they are usually fabricated in low cost. Based on the choices of printing materials and substrates, they can be flexible and non-toxic. In this presentation, I will introduce the design of a tiny and flexible stress detection circuit so that we can replace the smartwatch with a tiny circuit. The essential sensor used for stress detection is the electrodemo activity sensor, which measures the conductance of human skin. This value is related to the sympathetic neural activity. Regarding the detection algorithm, classic machine learning such as random forest and artificial neural networks are used. In this work, we leverage the printed electronic technology in wearable computing and replace the electrodemo activity sensor with the printed one. Moreover, we use the bandpass filter followed by a printed diode as the signal processor and the classifier. These figures show the proposed circuitry and the photos of the printed prototype. All components are made of graphene, which is a biocompatible material. We also want to highlight that this is a full analog, tiny, flexible, and low-cost stress detector. In the next slides, I will describe the design and optimization of the circuit components so that it can achieve the best detection performance. Rather than designing the filter in frequency domain, we model the filter directly from the hardware level in state space, and this is the system model of the bandpass filter. This figure shows the difference between hardware filtering and the frequency domain filtering. We can see from the green curve that the filtering built by the system model considers the nonlinearity of the system. Obviously, it respects the memory and inertia of the system components. Therefore, it would be more realistic to model the filter directly from the hardware level rather than from frequency domain, and thus the result will become more dependable. In terms of the objective of optimization, we formulate the objective function like this, where f summarizes the filtering behavior that is the system model, and p vectorizes the design parameters, namely the resistance and the conductance in this circuit. V in and y are the data and label provided by a certain dataset, and this means this optimization process is a data-driven optimization based on dataset. The second term functions as a sign of the first term. For example, when the subject is not stressed, the label yt equals 0, and in this case the second term equals 1, which means the output voltage should be minimized. In contrast, when the subject is under stress, yt equals 1 and the second term equals -1, which means the output voltage should be maximized. In this way, we can then use an additional threshold to do the stress detection, and classification. Since the system model is a nonlinear differential equation which has no closed form for solution, we use the CMAES algorithm to solve the optimization problem. CMAES stands for Covariance Matrix Adaptive Evolution, which is an evolutionary algorithm for complex and even yield condition problem. This figure shows the filtered signal with VSET dataset. The green curve is the filtered signal from optimized filter. As we can see, after the optimization, the output signal in stress time slots are increased and the signal in non-stress area are decreased. This facilitates us to do this classification by simply using a threshold. Regarding the threshold, to avoid low recall and low precision at the same time, we choose F1 score as the objective function, and since the threshold is a one-dimensional scala with limited range, we optimize the threshold value with grid search to achieve the highest F1 score. To preliminary test the feasibility of the design printed electrodynamic activity sensor, we asked the subjects to wear both PED sensor and the MTK E4 wristband simultaneously and to do their intuitive activities. We can see from figure A that the signal obtained by both devices are different because they have different sensor specifications such as different materials or different censorships. However, since both devices measures exactly the same physical property of human, which is the conductance, we believe that there is a simple transformation between both signals. Therefore, we built this linear model to transform the signal from E4 wristband to PEDA signal. Figure B shows both signals after the transformation, and we can see that by now they come up on the same scale. Furthermore, considering that the signal will pass through a bandpass filter for signal processing, we filter both signals. Finally, in figure C, we can find that the proposed EDA sensor can obtain comparable information to that of the state-of-the-art device, MTK E4 wristband. Regarding the future works, almost all the calculations in this work is simulated. But in the future, we plan to test the device in real world with experiments on subjects. Secondly, in this work, we only apply the design methodology on a second-order bandpass filter. But in the future, more sophisticated but dependable detection circuits can be designed. Moreover, we can also consider the protection error into the objective function of the design process. And finally, in this work, we use the external power supplier, but in the future, we can combine the circuit with printed or soft batteries so that the variability of the whole system can be improved. Thank you for your attention.